welcome to this class. So, in the last class we have discussed about different kind of patterns that we generally employ for casting process. So, this class we will start with the pattern allowances, like I have already told. Like there are different kind of allowances that we generally provide, like shrinkage or contraction allowance, machining or finish allowance, draft or taper, distortion or camphor, and shake or wrapping allowance. So, here you can see a brief overview of different allowances are shown over here. So, here you can see this is the first case, that is which is talking about shrinkage or contraction allowance. So, you can see the blue line inside it shows the required casting size, and the red line outside shows the actual pattern size. So, this is the shrinkage allowance. It varies from different material to material, like for example, in case of light alloys we generally provide 5 to 7% shrinkage allowance. So, that means the pattern needs to be bigger by that percentage compared to the end geometry in the cast part that we want to achieve. So, that after undergoing shrinkage the cast object is of required dimensional attribute that we are looking for. And then after this we are talking about the machining or finish allowance. So, again machining and finish allowance varies based on material to material and also based on component to component. Depending upon the accuracy in the surface finish we are expecting in the cast part. So, based on that, often there are complicated parts which are difficult to be resolved by melting casting process. There we add higher amount of machining allowance, so that that complicated contour we can machine out of the cast part once they are solidified. So, so this is basically the typical example of before and after machining geometries of the of the cast part. So, that is why accordingly the allowance has to be kept in the pattern. And then here comes the draft or taper allowance. So, this is for the case. So, you can understand that we are talking about that ramming the sand around the periphery of the pattern, and then we need to remove the pattern out of the sand bed, because then only the mold cavity is produced. So, when we are trying to take the pattern out of the mold cavity, so then that time, so this is basically the pattern. So, that time, and this is basically you assume that this is your sand bed. So, what happens the moment we are trying to take it out, then it can basically cause enlargement to the cavity laterally. So, that is what is not desired. So, then how we can achieve a smooth removal of the pattern out of the sand bed of the mold? So, by providing a appropriate draft or taper allowance, which makes the removal of the pattern after the mold is prepared easier, so that there is not unintentional dimensional increase which can cause faulty dimensions in the cast part. So, that is why so this draft or taper allowance is provided. And number 4 is the distortion or camphor allowance. So, this is your required shape. So, then if because of the contraction happens because during solidification freezing of the liquid melt in the form of cast component. So, then it can, there is a because of the residual stresses created during cooling of the cast object having different cross sections, there is often we end up getting a distorted shape of the component after cooling, after freezing. So, to avoid such kind of distorted shape that can cause total rejection of the cast part, because it cannot serve the dimensional attributes necessary for its intended application. So, that is why we provide a negative allowance to the pattern itself. So, this is called the cambered pattern. So, you can see a negative distortion is provided in the pattern itself, so that after undergoing distortion it can basically achieve the desired shape of the cast part that we are looking for. So, we want a straight shape like this one. If you compare with the required shape, so we can achieve the required shape by providing this negative distortion allowance. Okay. So, then only the number 5 is left. So, that is the shake or wrapping allowance. So, I can explain it to you with the help of this same geometry that is drawn over here. So, the shake wrapping allowance is basically happens during say even after if that. So, these are basically connected with the draft and taper allowance. So, if you provide a proper draft or taper allowance, then the need for providing shake allowance decreases. So, they are basically inversely proportional to each other. So, here you can see that if we provide a appropriate draft over here, so then the chances of enlargement of the mold cavity while ejecting the pattern out of the mold cavity is decreasing. So, that is why there is not much requirement of a shake or wrapping allowance, but there are instances where we cannot provide as much draft or taper allowance. So, in that case we need to compensate for the enlargement that may cause by the straight boundaries of the pattern by providing shake or wrapping allowance. So, that means that that is the enlarged part of the cast part that needs to be machined down after freezing of the component. So, these are some shrinkage machine contraction allowance. So, as I told you that there are three kind of shrinkage basically. One that is experienced by the liquid melt when it is cooling down from superheated molten state to its liquidus temperature. So, it is called liquid shrinkage. And so, if I draw over here, so then you can understand. So, this is basically the temperature regime. Assume that this is the liquidus temperature T L, this is the solidus temperature of the alloy melt T S, and this is the superheated pouring temperature T P. So, until this is your liquid shrinkage L S, and this is here is the between the liquidus and solidus temperature is your solidification shrinkage, say L S F solidification shrinkage, and then up to this much, that means its temperature below the solidus temperature to the room temperature, the solid object is experiencing solidus shrinkage. Okay. So, that can be determined as shrinkage F, solid shrinkage. Okay. So, so this is the so reduction in volume caused when metal loses temperature in solid state. So, for different materials there are separate shrink rulers are available, which helps in providing the appropriate shrinkage needed in the individual materials under consideration. So, so you can, there are some typical shrinkage allowances provided for different grades of the material, like for in case of grey cast iron, and also in case of cast steel, and in case of aluminum and magnesium they are compared. So, you can see the shrinkage allowance needed in case of like cast steel is much higher compared to what it is needed in case of grey cast iron. So, and also it not only depends on the material, but also depends on the dimension of the object that is we are going to cast. Okay. So, this is how we provide shrinkage allowance to the cast geometry. So, so these are some other details, like for cast iron how we basically calculate for the shrinkage. So, shrinkage allowance depends on the coefficient of thermal expansion of the material. So, a simple relation indicates that higher the value of alpha, that means the coefficient of thermal expansion, more is the shrinkage allowance. Okay. Because that means if the value of alpha is more, there is more chances of contraction of the component upon solidification. So, that is why that contraction need to be accommodated by providing appropriate shrinkage allowances to the pattern. So, for a dimension L, shrinkage allowance is alpha L theta f minus theta 0, where theta f is the freezing temperature and theta 0 is the room temperature. So, it is talking about the solid shrinkage. So, that can be adjusted by by this much shrinkage allowance. So, we provide shrinkage allowance to the pattern to cater to the need of solid shrinkage. That means, the shrinkage undergoes by the object below its solidus temperature to the room temperature, whereas to feed to the liquid and to the solidification shrinkage, we provide riser within the mold cavity. We will also discuss about riser design later in the class. So, I mean the next is machining allowance. So, we have already discussed about the necessity and importance of providing machining allowance to the pattern. So, this table shows, I mean, for your knowledge about the machining allowance that is generally provided for different materials and also for different I mean locations within the cast object that are being manufactured out of these materials. So, next the draft allowance also has been discussed. So, this table shows you the amount of draft allowance provided for different pattern materials, like when pattern is made of wood. So, then the I mean the draft allowance is much higher I mean compared to the when the I mean this pattern is made of either metal or plastic material. Okay, so, distortion allowance also we have discussed earlier. So, here it is shown in much detail. So, I mean in this in case of distortion, the vertical edges will be curved or distorted. So, this is prevented by shaping pattern which converts slightly inward, so that the casting after distortion will have its sides vertical. So, I mean so the distortion in casting may occur due to internal stresses like residual stresses I talked to you before. So, these internal stresses are caused on account of unequal cooling due to variable cross section within the cast object, and their non-uniform cooling causes residual stress generation, and which in turn causes distortion of the cast part upon solidification. So, how to prevent it? Providing sufficient machining allowance to cover the distortion effect, providing suitable allowance on the pattern which is called camber or distortion allowance. That means, the negative I mean allowance that is provided by making a pattern distorted at the beginning in the opposite way what it is expected to get distorted, I mean in the opposite direction the pattern is made distorted, so that it end up after freezing the actual shape. For example, it is shown in case of this U. So, the pattern is provided with camber allowance. So, that is the negative I mean distortion provided to the pattern itself, so that after undergoing distortion it can achieve the desired shape, that means a straight U it can become out of the cast part after solidification, and then the intended job is satisfied, because it can match the intended I mean shape of the part to be made. So, the shake or wrapping allowance. So, like I told before that they are basically I mean should be of higher amount if there is sufficient draft allowance is not provided. If there are sufficient draft allowance is provided to the pattern, then the shake or wrapping allowance goes down. And so, the pattern materials. So, patterns for sand castings are subjected to considerable wear and tear due to ramming action that is required and the abrasive action of the sand. So, should be impervious to moisture because of changing surroundings, and they are generally made of wood, metal, plastic or plaster and synthetic materials. So, these are I mean so woods there are different kind of woods those which are used for as a pattern material, like white pine, sugar pine, etc., and also mahogany at times. So, I mean so for large castings, metal such as cast iron or aluminum, when metal pattern are cast from the wooden master pattern. So, I mean metal patterns are being used when basically the casting is large in size, and also there is mass production is involved, because in that case the repeated use of the wooden pattern can cause wear and tear to the pattern, and it can also I mean decrease the I mean sustainability of the process. So, only thing that needs to be taken care of, that when we are using metallic patterns, in that case we have to have a double allowance. That means, because if we are making metal pattern, then it will also undergo shrinkage while we are manufacturing the pattern, and then we I mean cavity we are trying to make with for solidification of the actual cast object, that material will also undergo shrinkage during solidification. So, that is why there has to be a double shrinkage allowance incorporated in the pattern geometry, so that we can achieve the desired geometry of the cast part upon solidification. As now we will move to the core and core prints. So, core, as we have already discussed, core are basically used for getting the hollow shapes made within the cast object, and I mean, so when coring is required, provisions must be made to support the core within the mold cavity, and core prints serve the purpose of supporting the core within the mold cavity, so that it does not get dislodged from its original intended location within the mold cavity. So, in that case, for example, this is a I mean straight cylinder I mean hole that is needed in this case. So, I mean, so this is the core placed inside. So, if it is not supported by core prints, so this can cause a I mean eccentric hole in the component component upon solidification, and which can otherwise cause rejection of the cast part, because there is no means even by doing significant machining that to achieve the desired dimension, because if we try to machine to make it straight, in that case we will end up enlarging the dimension of the hole, and that will not be able to assemble in the desired in service condition. So, that is why we have to place the core effectively within the mold cavity, and that is why we need to take the help of core prints. So, core prints are added projections on the pattern which are designed at the beginning on the top of pattern or on the appropriate locations within the pattern, which serves as the seats of where the core rests within the mold cavity, and so that it can withstand the metallostatic forces exerted by the flowing liquid melt which is getting poured within the mold cavity. So, the size and shape of the core print must be adequate to support the core's weight during the casting operation. Yeah, so these are different examples of cores like horizontal core, vertical core, also balance core, and also the the hanging core, which are also quite a tricky kind of cores, because their position determines the success of the dimensional attributes of the cast part that is being manufactured. And so, apart from core print, there is a concept of chaplets which are used to support the core and are positioned between the core and the mold wall. So, that means, so this is a typical example of chaplet. So, you can see that even so this is a case where it is basically the case of core print, and then when only core print is not enough to position the core within the mold cavity, because in this case you can see this core is kept like a cantilever beam, that is it is a overhang. So, you have a provision of supporting it with the help of core print at one direction, but not in the other direction. So, because of this overhang, it can still be dislodged at the onset of melt flow within the cavity, and that can cause a tapered hole. So, to avoid that, we use chaplets which are often made of the same material for which we are going to make the cast object, so that they can serve their intended purpose of holding the core in position till the melt is flowed in within the cavity, and then later on they can also fuse within the melt, and they can so that they does not leave any defect within the cast object, which can cause sacrifice the mechanical integrity needed in the cast part. Okay. So, now we will go into the individual functional parts of the gating system. Like we have discussed before, the functional parts are sprue, pouring basin, sprue base well, runner extension, and ingate and riser, which are systematically shown over here. So, here these are the open or top riser, which are basically open to the atmosphere. These are having almost the same exposure at the top of the mold cavity like the sprue itself, and often they are positioned at a same metallostatic head and exposed to the environment. So, these are called open or top riser, and these are basically the ingate where from the melt is getting entry into the mold cavity. So, there are multiple ingates for a large casting. So that it can facilitate simultaneous entry of the liquid melt throughout the mold cavity, so that there is uniform solidification across different parts, and which can also cause the homogeneity in microstructure and properties of the part upon solidification. So, I mean the objective of the gating design, so design the gating element such that the liquid metal can enter into the cavity with optimum velocity within a given time without causing turbulent splashing and erosion, because turbulent splashing certainly causes gas absorption and defect formation within the solidified object, and also it causes mold erosion, and mold erosion is linked with the enlargement of the mold cavity, and that can cause. So, this is say it is a mold cavity which is needed for the cast object because of turbulent entry of the liquid melt. If say if it is poured by top gating, that we will discuss after this, then it can erase and it can cause erosion, and it can basically enlarge the cavity by a significant extent, and which can cause the dimensional attributes to achieve in the cast part significantly degrade. So, design the gating element so that pure liquid metal can enter into the cavity without air aspiration effect. So, these are the different need for the gating design to be done successfully. However, we have to think about the casting yield also, because gating design, although these are serving as a functional part to the solidifying part during filling stage. However, they serve as a non-functional part upon solidification of the part, and then they are needed to be removed from the cast object by fettling process. So, the casting yield can be expressed as volume of casting divided by volume of casting plus volume of the gating elements. Gating elements means the combined weight of the sprue, ingate, runner, runner extension, etc. So, we have to be careful that we do not end up putting so much material in analogous part of the solidified object, the gating system. So, because that can decrease the casting yield significantly. So, now we will try to discuss individually about the importance of the different subsystems of the gating system. So, here comes the first in the list is pouring basin. So, as I told you before, the pouring metal so molten metal is directly poured into the pouring basin, and then it can cause decrease of the melt velocity, so that it does not cause turbulent entry into the sprue. So, the velocity can be regulated, flow rate can be regulated, and also this you can see there is a hump at the entry from the pouring basin to the sprue. This can cause act like a strainer. It can trap some inclusion or darts which are present in the melt and does not allow it to go into the stream through the melt stream which joins into the sprue, and thereby it can facilitate cleaner melt entry into the mold cavity, and also it can help in like a reservoir, so that from where it can move smoothly into the sprue. So, these are the essence of pouring basin, and then here comes the sprue. So, here the sprue is the channel through which the molten metal is brought into the pattern plane, where it enters the runners and gates to ultimately reach the mold cavity. So, so the how to determine the dimensions of the sprue. So, we can basically do it quite effectively by applying Bernoulli's equation. So, Bernoulli's equation, I hope you are already aware. However, I am writing over here. So, it is so Bernoulli equation can be expressed and can be applied between two locations within the flow path. So, it can be expressed as P by rho g plus V square by 2 g plus z is equal to constant. So, this is how we can write the Bernoulli's equation. So, and we can apply it to design the different sections of the gating parts gating system. So, the exact tapering can be obtained by the equation of continuity, denoting the top and choke sections of the sprue by the subscript T and C. So, basically here this is the top section T, this is the choke section C, and so here ATVT is equal to ACVC based on the continuity equation. So, since the velocities are proportional to the square of the potential heads, it can be derived from Bernoulli's equation that AT is nothing but AC Vc by Vt. So, how we are arriving at this expression? So, AT is equal to, so from here we can get that AT is equal to AC Vc by Vt. So, that means AC root over 2 G H C by root over 2 G H T. So, that means from here we can get it becomes equal to AC root over H C by H T. So, this is how we can determine the dimension of the sprue top if we know the dimension of the sprue choke. And I mean, so this is how this is the I mean we can determine the velocities I mean if you know the velocities also, or the height. If you know, then from their height we can calculate the, if we know couple of dimensions we can get the other dimensions based on that. So, often we are I mean dealing with the tapered sprues, not straight sprues, because the straight sprues cause air aspiration effect, and that is the location where the air bubbles can be entrapped within the mold cavity, and that is a very significant and damaging defect. This happens due to flow separation, and because I mean the flow, so that is why we need to always ensure that the melt remains, I mean it flows full within the different subsections of the gating geometry. Otherwise, there will be flow separation and there will be chances of air aspiration, and that can cause bubble damage or defect formation within the cast part, which can significantly downgrades its mechanical property and structural integrity. Okay. So, here the square root suggests that the profile of the sprue should be parabolic if exactly done as per the above equation, but making a parabolic sprue is not convenient in practice, and therefore, a straight taper is preferable. So, it has been found in practice that a straight tapered sprue is able to effectively reduce the air aspiration as well as increase the flow rate compared to a cylindrical I mean straight cylinder sprue. So, metal at the entry of the sprue would be moving with a velocity of root over 2 G H, and here I mean you can see hence A T is equal to root over H T by H. A T that means the area at the top. So, here capital H is the actual sprue height I mean which is I mean small h plus capital H. So, this is the H T. So, this is basically the head I mean of the metal from the I mean sprue entry sprue base well to the I mean that bottom of the reservoir, that is I mean bottom of the I mean top pouring basin. So, this is basically the pouring basin. So, that is marked here by capital H, and the height of the liquid melt within the pouring basin, that means from the base to the free surface of the melt within the pouring basin is marked as small h over here. So, I mean so the aspiration effect I mean we can explain from here. So, it is basically, so we can understand it from the case of this I mean straight cylinder sprue. So, you can see, so here this is the free surface of the melt is kept at I mean marked as position 1, and then so here at the I mean just at the, when it is entering into the I mean sprue there it is marked as 2, and then when it is just coming into the I mean mold cavity it is marked as 3. So, these are the 3 important locations. So, if we apply Bernoulli's equation between the point 2 and 3, then we can understand that why we I mean cannot have a straight cylindrical sprue in I mean casting processes to avoid I mean air aspiration effect. So, so if we need to apply here the Bernoulli's equation between point 2 and 3, so then we have to so P 2 by rho g plus V 2 square by 2 g plus H 2 is equal to P 3 by rho g plus V 3 square by 2 g plus. So, here because there is no I mean height, so because it is kept at the reference position, so the H 3 is basically 0. So, here and also I mean because it is exposed to the I mean environment. So, here the P 3 becomes 0. So, this term gets cancelled off, and here because I mean so we can get the value of V 3 and V 2. So, V 3 again it is I mean open to the exposure. So, we can assume that V 2 is equal to V 3. So, these terms gets cancelled off. So, then P 2 by rho g is equal to minus H 2, right. Okay. So, I mean so then P2 is equal to minus rho g H2. So, then this is the problem with the straight taper screw, straight cylinder screw, that is shown over here. So, you can see the pressure becomes negative at point 2. So, then there will be the every chance of air aspiration, and that will cause defect formation within the cast object. So, that is why we cannot have straight cylinders as proved geometry. So, what is the remedy? The remedy is shown in the next slide, where that we can go for this tapered cylinder, although the actual shape of the sprue should be parabolic. However, that becomes very difficult to machine, and that is why the nearest best solution is to have a tapered cylinder as a sprue geometry. So, so now I mean if we need to get the dimensions of the this tapered cylinder, that how much taper it should be. So, then we need to apply the Bernoulli's equation again between point 2 and 3. So, then what we can write? So, here we can write, so P 2 by rho g plus E 2 square by 2 g plus H 2 is equal to P 3 by rho g plus B 3 square by 2 g plus. So, here because it is the end. So, from this is from the reference point. So, here H 3 becomes 0. Okay. So, here if in the limiting case, so P 2 becomes equal to P 3. So, then so these two also gets cancels out. So, then we arrive at this expression from here. So, P 3 by rho g gets cancelled out. So, then you can see that this is the expression it becomes, that means V 3 square by 2 g is equal to V 3 square by 2 g is equal to V 2 square by 2 g plus H 2. Okay. So, if we multiply this with g, then we can arrive at this expression. So, that means V 3 square by 2 is equal to V 2 square by 2 plus g H 2. Okay. So, then so this is the expression that we can get, and then so this is what is shown over here. Okay. So, then so as we know based on the continuity equation that V 2 A 2 V 2 is equal to A 3 V 3. So, then so then V 3 is equal to A 2 by A 3 into V 2, or we can express V 2 as A 3 by A 2 into V 3 from here. Okay. So, here this is the this ratio between A 3 and A 2, that means the cross sectional area at location 3 and the cross sectional area at location 2, we can designate it as R. So, that means V 2 becomes equal to R V 3. So, combining above two equation and basically we already now we have get the value of V 2 as R V 3, and then if we can place this over this expression, that is V 3 square by 2 g is equal to V 2 square by 2 g plus H 2. So, if we put this value back here, so then we can end up getting this expression. Okay. So, that means V 3 square by 2 g plus H 2, V 2 is equal to R V 3, that means R square V 3 square by 2 g. Okay. So, from here we can get the value of R square, which comes as R square is equal to 1 minus 2 g H 2 by V 3 square. So, now if we apply the Bernoulli's equation again between points 1 and 3. So, so here is basically the point 1 and this is the point 3. So, then we can get, because all other terms gets cancelled out, because here it is exposed to the environment, again here it is exposed to the environment. So, P 1 is equal to P 3 is equal to 0, and then so we can finally arrive at this expression. So, because at V 1 it is the head of the metal does not get changed. So, we can assume that V 1 is also 0. So, that means the initial two terms of the Bernoulli's equation cancels out, and the point 1 is placed at a height H t from the reference. So, G H t is equal to V 3 square by 2. So, here the pressure term cancels, and also the, because it is placed at the datum. So, the datum head is also cancelled out. So, then we know that GHT is equal to V3 square by 2. So, putting in R square equation, so I mean we can get that R square, as we know, that 1 minus 2 G H 2 by V 3 square by 2. So, from here we know that V 3 square is equal to 2 G H T. So, then if we put this value back in this equation, then we can get R square is equal to 1 minus 2 G H 2 by 2 G H T. So, that means R square is equal to 1 minus H 2 by H T. So, H 2 is nothing but H C. Okay. So, from here we can so you know, not that, I mean we can get it from the, I mean, so continuity equation we can achieve that. So, that means, I mean we have already evaluated it before, yeah, from here. So, then we can place it as H 2 by H T as equal to, I mean 1 minus 1, I mean H T minus H 2 by H T. So, H T minus H 2, that means here it is available from, yeah, H T minus H T. So, this is the total H T, H 2 is this much from reference to this. So, that means H T minus H 2 becomes equal to H C. Okay. So, here we can just replace it by H C. So, that means H C by H T. So, that means R square is equal to H C by H T. So, we can get R is equal to root over H C by H T. Okay. So, from this expression we can understand that although the shape of the I mean sprue should be parabolic, but this tapered cylinder is the actual realistic dimension that we can go for I mean sprue manufacturing. And also we can also design the sprue based on applying the Bernoulli's equation, and then we can get the design attributes of the sprue. That means we can identify that how much taper is needed to achieve the desired sprue geometry. So, with this I am stopping with this class, and in the next class we will go ahead with the further sections of the gating geometry that is needed to achieve a sound casting. Thank you.